Alright, in this problem we've got a half full spherical tank with radius 8 and it's half full with a fluid of density 50. And for density I use the variable rho, and rho is equal to mass per volume, work is equal to force times distance, and force is equal to weight. For this class, it's okay to use all of those. If you go to someone else, maybe in another science class, maybe in another math class, they say, don't do that, that's wrong. But for what we're doing today, all of this is okay. I start off by rearranging rho is equal to mass per volume into mass is equal to rho times volume, which is another thing some people might not like, but for as far as this problem is concerned, mass is equal to weight. So we have mass is equal to rho volume, so our force, which we said was the weight, is equal to rho volume. Here's a little side view of our sphere. I'm going to be using the volume is equal to the area in terms of y, dy, definition of volume, and for that I'll be taking vertical slices. You can see that dy. I just put a rho inside the fluid so that you could see that's how full it is. I said the radius is r, and I took the origin of my coordinate axis to be at the center of the sphere. You could do this at the bottom, at the top, at the center. Don't do it at the bottom or top at all, unless you are like 100% sure that it's going to be way easier if you do it that way. If you ever see a sphere like this, and or in this case where you got to calculate work, always put it right at the center. The origin of your coordinate axis. Here's a top view of the top slice. So you can see I'm taking dy's, starting right at the middle because the tank is half full, and I'm going all the way down. So if I just do like a little top slice of that, you can see r over there is still my radius, and the center is right there at 0, 0. Now that's just a circle centered at the origin with radius r. The formula for that is x squared plus y squared is equal to r squared. And since I'm using dy, I'll be using the area in the y, and that is that means that we'll want our answer, or we'll want our equation to be in terms of y. So I have x is equal to square root of r squared minus y squared. Remember that r is a known value. I'll try not to plug in anything for anything, just so it'd be as generalized as possible. You can always plug it in at the end, but r is 8. Moving from there, I just made sure to explicitly say that's not just x, that is the radius of a slice is equal to the square root of r squared minus y squared. I specifically said radius of a slice because it's just radius. You see there's already r in there, right? But that is the radius of a slice of a volume of water. And we're going to be using that slice, summing up those slices in an integral later, so that we get the entire volume. Right here, we said that the radius of the slice is equal to the square root of r squared minus y squared. So using the disk method, we have the volume is equal to pi square root of r squared minus y squared squared dy. That is the volume. Okay, so now that we have the volume and rho is given, we do in fact have the force, because the force was just, we were going to say the weight, and the weight was analogous to the mass, and the mass is rho v. So we have an equation for v, we're given rho, we essentially have the force. So now we just need to find the distance and we can calculate work. So you might have already seen, I wrote the distance as r minus y. So why is that? That's because if we're going back over here, we're going to take the distance to be, it's got to be that, I think oil needs to be pumped out through the top, and the top is a distance r away. And from the center, it's always going to be a distance r away. So the fluid is always going to need to move at least r. Starting from there and going down, we're going to get coordinates essentially as, well, at the very top, we'd have a coordinate of 0, 8, and then at the center, we've got coordinates 0, 0. So that's how you can see, hey, it's the radius of a sphere, but also using distance formula, it is a distance of 8 away at the very least always. From there, as you go down, you get an x-coordinate of 0 all the way down, and along the way, you're going to get y-coordinates. I say negative, not negative, just y-coordinates of y. And then the distance from the top of the sphere, which is 0, 8, to any point straight down to where our slice of water is going to be 0, y. So the difference of that, or using the distance formula, or just seeing the distance, you should get the 8 minus y. 8 just because our radius is 8, it'd obviously be whatever the radius is minus y, and that's what I wrote down because I didn't try and keep it generalized. And now we can just plug in everything for our work. Our work is the integral from negative r, which is negative 8, to 0 of rho times pi times quantity r squared minus y squared times r minus y dy. So just make sure we get everything there. We got pi r squared minus y squared. That is the area of a slice. That's the area of a disk. The area of that disk times the dy, that gives us the volume. The volume times our rho, which is 50, that gives us our force. And then our force times r minus y, which is the distance, gives us the work. So, yeah, that's our formula for work. I think maybe somewhere in your book, they may have shown that dW is equal to force times ds for displacement, or dx. But if you just take the integral of both sides, you get W is equal to the integral with respect to x or y or whatever variable you're using. All right, that should be it. Let me know if you got any questions.